morning. Dr. Rafich here from Vet Triage. It is Friday, January 17, 2025, 9:25 a.m. Pacific Time. We are continuing on October 2024 edition of Veterinary Surgery, and we are going to be talking about the mechanical comparison of straight and pre-bent interlocking nails used for stabilization of a tibial gap fracture model. So for those who don't know what an interlocking nail looks like, here's a picture. They place this large metal rod in the middle of the bone, and then you see at the top and the bottom of the bone there are two nails, two at the top, two at the bottom, that interlock with the nail. So it's the interlocking nail is the construct here, and it's takes a steep learning curve, specialized equipment, but it's a very strong construct. It's just not used that much because it takes a lot of learning for it, anyway, but it's a very cool, very strong. It kind of combines the benefits of external skeletal fixation with internal skeletal fixation. This comes out of the College of Veterinary Medicine, Michigan State University. The objective was to compare the mechanical behavior of straight and pre-bent interlocking angle stable nails for stabilization of canine mid-diaphyseal tibial fractures. It's an in vitro experimental study with 5 per group. The methods included bent nails were contoured to match a 10-degree tibial recurvatum of a mid-sized dog. In the picture below there, you can see what recurvatum and procurvatum typically look like. Dogs have a natural bend to their bones, some more than others. Obviously, a Labrador Retriever will have more straight legs straight bones than a Bulldog will. And so they want a 10-degree tibial recurvatum. Constructs were subjected to cyclic eccentric compressive loads, followed by ramp load until failure. Construct compliance, maximal compressive load, and resistive torque, as well as yield load and angular deformation at 450 newtons were compared. Results show that compliance was 45% lower in the pre-bent than straight, meaning that they are more stiff. Constructs in the bent group sustained 20% and 34% greater maximum and yield loads specifically than the straight. Maximum resistive torques were similar between groups. At 450 newtons, sagittal plane angular deformation increased from 0 degrees to 4 degrees in procurvatum with the straight group, and decreased from 10 degrees to 8 degrees in recurvatum in the bent group. Construct yield failure occurred at the nail isthmus in both groups. The conclusion was that the results demonstrate in a tibial gap fracture model, pre-bending provides mechanical advantages by increasing the ability to resist bending resulting from eccentric compressive loads. So a lot of jargon here that I'm not going to go through. A lot of it's very engineering, structural, but the important thing here is to note that maybe pre-bending these interlocking nails should be considered when you're working in a real live case. Introduction. Tibial fractures are common and account for 20% of all long bone fractures. Of those, 70 to 80% involve the diaphysis. Interlocking nails is considered the standard of care for people. One potential limitation of the tibial nail osteosynthesis is acute postoperative yield in both procurvatum and, to a lesser extent, valgus. Under in vivo loading conditions, a straight nail is inherently subjected to eccentric compressive forces, which generate deleterious bending moments in the sagittal plane. The magnitudes of these moments is accentuated by the asymmetrical muscle distribution along the caudal and lateral tibial cortices. Because of the relatively larger size of the caudal versus lateral muscle groups, meaning gastrocnemius and tibial cranialis, respectively, one should anticipate greater bending moments in the sagittal plane rather than transverse. Furthermore, these bending moments generated during muscle contractions are unopposed, since no muscles are present along the medial and cranial tibial cortices. In a previous in vitro study, they showed that tibial nail constructs are more compliant in the craniocaudal than medial lateral plane. The benefits of this technique involve preservation of the cranial cruciate ligament integrity, via nail insertion cranially to the ligament footprint, and restoration of the normal tibial anatomy, including the tibial plateau angle. And then here is a picture of what these constructs look like in different points of views. Regarding materials and methods, mid-diaphyseal tibial fractures in mid-sized 35 to 40 kilogram dogs were used. The fixtures were fitted using CAT scan based on 3D printed segments representing the proximal and distal thirds of the mid-sized dog tibia. And here's an example of the 3D printed things there and the way they inserted the constructs in that machine. In contrast, the bent group was gradually bent to 170 degrees in the sagittal plane. The apex of the bend was located at the center of the nails. That angle closely approximates an anatomical 10-degree tibial recurvatum of a mid-sized, non-chondrodystrophic dog. Regarding the fixture design, they had specimens were cyclically tested non-destructively in a compression from 10 newtons in preload to 300 newtons, which is about 75% of a 40 kilogram dog body weight. Cyclic tests were conducted under load at 1 Hertz cycle rate for 10 cycles using a sinusoidal waveform protocol. Actuator displacement, compressive load, and resistive torques were recorded at a sampling rate of 100 Hertz. Failure was defined as a 25 millimeter actuator displacement, as this resulted in 25 degrees and 15 degree yield angles in procurvatum and valgus respectively, which closely replicated straight nail yield failure angles observed in clinical cases. Regarding outcome measurements, compliance rather than stiffness was determined since cyclic tests were conducted under load control conditions. Compliance was defined as the slope of the displacement versus load curve generated from actuator and linear load cell data during the 10th cycle and was computed between 150 and 250 newtons using linear regression with a correlation coefficient greater than 0.98. And here is the example of the interlocking nail in the bone, and then here's what the machine looks like where they tested all these forces. Regarding the nail yield point, nail yield was obtained during failure tests and was defined as the point where the specimen first transitioned from elastic to plastic deformation. This point represents the beginning of a reversible implant deformation. The yield point was estimated at the intersection between the load versus displacement curve and its linear region or stiffness offset horizontally by 0.1% strain. And here you can see the different graphs that shows how the constructs would fail over different forces. Failure mode was described as either bolt shear or nail yield. Okay, results. Compliance, maximum compressive yield load, and angular deformation in the sagittal plane at 450 newtons were significantly different between groups. There was no difference in resistive torque between groups. Compressive force required to straighten the bent nails was statistically similar to the maximum compressive force in that group and was greater than the maximum compressive load sustained by straight nails. The construct compliance was 46% less with the bent compared with straight. The maximum compressive load was 20% greater in bent versus straight. Maximum resistive torques were less than 0.3 nanometers in both groups and did not differ significantly between groups. Yield load was 34% greater in bent than straight constructs. The compressive force required to strain the bent nails, there was no significant difference between the compressive force required to straighten the bent nails in the sagittal plane and the maximum compressive force sustained by the nails in that group. However, the bent nail straightening force, which is 985.1 newtons, was significantly greater than the maximum force sustained by straight nails versus the 842.6 newtons. Regarding angular deformation at 450 newtons, the mean absolute angular deformation in the sagittal plane was significantly greater by about 50% between groups. Importantly, while deformation in the straight group induced irreversible procurvatum, Bent nails remained in recurvatum, albeit with a reduction of the nail angle from 10 degrees to 8 degrees. Conversely, angular deformation in the transverse plane, valgus, showed no significant differences between groups. Regarding failure mode, all constructs failed via plastic deformation at the nail isthmus, with no differences in failure between groups. None of the blocking bolts sustained any visible structural damage. Okay, discussion. In a tibial fracture model, when compared to straight nails, pre-bending confers superior mechanical properties to the nail, including reduced compliance and increased maximum compressive and yield loads. And that's the end point of this whole study is that one line. These findings are highly consistent with clinical outcomes of both pre-bent versus straight tibial nail application. This is internal unpublished data and personal communications with other surgeons. The significantly higher compliance of straight constructs likely contributes to the yield failures reported when straight nails are selected for tibial osteosynthesis of comminuted mid-diaphyseal fractures. To reduce the risk of tibial nail yield failure, pre-bending should be considered, particularly when a less compliant construct is desired. During loading, straight nail deformation in procurvatum gradually increases the magnitude of the moment arm from 21.65 to 24.9 millimeters, which is a 15% increase. As the center of the nail moves away from the construct loading axis, the bending moment to which the nail is subjected increases, which in turn increases deformation. While this phenomenon is reversible during non-destructive cyclic loading, it becomes irreversible once nail yield has been initiated at 450 newtons. During loading, the bent nail recurvatum decreases from 10 degrees to 8 degrees, which corresponds to an increase in moment arm magnitude from 13.6 to 15.2 millimeters, which is a 12% increase. While this increase in moment arm also increases the bending moment to which the nail is subject, albeit to a smaller extent than with straight nails, it is important to note that the nail retains its initial recurvatum orientation and therefore its ability to efficiently resist bending. Just telling you it's stronger again if you pre-bend. Interestingly, while angular deformation at 450 newtons was significantly different between groups in the sagittal plane, pre-bending did not affect valgus deformation. Since valgus deformity, albeit to a smaller extent, has been reported clinically in straight nails, one could speculate that pre-bending the nail in both sagittal and transverse planes could theoretically further improve the mechanical benefits of nail pre-bending. However, this modification would induce a varus angular deformity, which would negatively affect limb function. Additionally, pre-bending the nail in two planes might increase the challenge of locating the distal nail cannulations during nail placement. Both groups eventually exhibited yield failure, with the apex of the deformation occurring at the nail isthmus. This is consistent with clinical observations of straight nail failure and was anticipated since the nail's smallest area moment of inertia, and therefore the weakest point, is located at its center. Furthermore, when performing bridging osteosynthesis, the nail isthmus is also located at the mid-diaphysis where most tibial fractures occur. Finally, another limitation of the study is that we only tested the observed nail recurvatum of 10 degrees. While outcome could be different with greater recurvatum, this technique has been used successfully by the author in chondrodystrophic dog breeds where the recurvatum is 25 to 30 degrees. So that's it. That's a study. It's a solid study. And thanks for those who watch the channel and support it. We'll see you again tomorrow for another one. Take care.